Hello everyone, myself Rajesh Prasad, working as professor in CSE department at AKGEC Ghaziabad. So I'm going to discuss string matching using finite automata. So we are going to see how finite automata can be used in finding a pattern inside the text. So we know that all of us, we know that finite automata has different like NFA and deterministic finite automata and NFA with epsilon. So this category of finite automata is going to be used in the matching process. Yes, so in this process, as we know that we are going to discuss like pre-processing. Matching here is going to be done in two stages. First one is pre-processing and second one is matching. So generally pattern is going to be pre-processed, and once we are done with the pre-processing, then that pre-processing is going to be used in the matching process, right? So for this pre-processing purpose, I am going to define suffix function for a given pattern. So what is suffix function? So actually suffix function is a map from sigma star, and sigma star is any finite alphabet, right? 2, 0, 1 to m. Yes, such that sigma x is the length of longest prefix of p, that is also suffix of x. Yes. So for example, if you see p equal to ab, right? And I'm interested in finding sigma ccab. So it is saying that sigma x, this is x, is the length of longest prefix of p, that is also suffix of x. That means we are interested in its suffix or we are interested in prefix of p. See, what are its suffixes? Its suffixes are b, then ab, cab, and then ccab. And which of this suffix is going to be part of the prefix, maximum length, right? So B is like we start from CCAB. CCAB is not part of the prefix, yes. CAB is not part of the prefix. Of course, AB is part of the prefix. That means its length is going to be 2. This is the suffix function. So on the other hand, suppose you have ABA in the reference of the AB itself, right? So what are these suffixes of ABA? Its suffixes are A, then BA, then ABA. These are the suffixes of X. So which of these suffix is going to be part of the prefix, right? So A, yes, we start from the longest one. ABA, no, ABA is not part of the prefix. BA is not part of the prefix. Of course, A is part of the prefix. So definitely its length is going to be 1. Yes, so this is the idea. Now, again, if we are interested in finding prefix, suffix function of ABB, so we enumerate its suffixes. What are its suffixes? B, then BB, then ABB. So you see this, and your pattern is AB. So we can see that none of the suffix is going to be prefix of P. So definitely its epsilon is always there. So its length is going to be 0. None of the prefix is found to be like suffix is found to be prefix of P. So it is going to be 0. So I think this is clear. So if we, so objective is to first compute suffix function for the pattern. Okay, so let's see. So here in this string matching algorithm, we are given a pattern, and objective is to compute suffix function for this pattern. So how to compute suffix function for this pattern is the same thing. Sigma x we have computed is length of longest suffix of x, which is also part of the prefix, right? prefix of the P. P is given. Look suffix into this and check prefix into P. That is the idea. So in this one, what we are going to have? We are going to have a Q, which is set of states. States are numbered from 0 to length of the pattern. So corresponding to each symbol plus a 0 is starting state and M is the only accepting state. Yeah. So the transition function for Q belong to Q and A belong to sigma is defined as like this. See, this is the transition function. So delta, you are in a Q state and input is A, right? So delta QA is going to be sigma PQ of the A. That is it. And after computing this, whatever number is coming, that is going to be the transition function of A. Let's have one example. So suppose you have this pattern, right? Sigma P A B A, pattern is ABA BA CA, right? Yeah. Let's draw it separately. So we are starting from state number 0. Clear? We are starting from state number 0. Yes. So, and we can see that different inputs on states are A, B and C. So, let's start from sigma, computing sigma 0, state number is 0 on A. So, by the definition, sigma QA is, delta QA is sigma PQA. So, this delta Q0 is sigma P0A. Clear? Yes. So P0 means epsilon, right? So sigma A. So this is the value. And we are looking for its suffixes, which is part of the prefix of the pattern A. So you can see that its suffixes are epsilon and then A. Clear? Its suffixes are epsilon and A. Definitely epsilon is the trivial suffix, not an issue. So this A means that yes, this is A and A is going to be the part of the prefix. Yes, so its length is 1. So that means if you start from 0A, you are reaching at first state. This is the state number. Yeah. 0A, you are reaching at state number 1. This is the one, right? Yes. Again, start from sigma delta. If you start from 0 and then look at B, transition on B, so this is going to be sigma P0B. Clear, class? So P0 is epsilon, so sigma B. That means its suffixes are B, its suffixes are B, then epsilon. Of course, B is not part of the prefix. So epsilon is part of the prefix. Its length is 0. So that means this is going to be 0. On 0, you are going to be 0 on B. So generally, we are skipping this transition. We don't want to see this transition. So same thing, if you look at the sigma like delta, if you look at the delta, P0 means like 0 and then C. Same thing, sigma P0 C. Clear? And P0 is epsilon, so this is C. C is of course not part of the prefix, so its value is going to be 0. Clear? Yeah. So we are done with this transition. Okay. Now we are at 1. So 1A, that means let's check this row. 1A. So delta 1 comma A. Its meaning is simple. Sigma P1A. P1 is A, right? Yeah. So means that delta P1 means A and A. Clear? Yeah. So its suffixes are epsilon, A and then double A. So of course, double A is not part of the prefix. A is the part of prefix, yes. So definitely its answer is going to be 1. So this is going to be 1. So 1A is 1. It's clear. Yes. So now, and now 1B. Let's say 1B. Delta 1B. So if you go and compute delta 1b, what is delta 1b? Delta 1b is of course sigma P1b. P1 is A, means that sigma AB. So what are its suffixes? Its suffixes are B, then AB, and then epsilon. Of course, longest suffix is AB, which is part of the prefix, right? Prefix of the pattern. So its length is going to be 2. So this is correct. Same thing in the similar fashion, 1 and C is going to be 0. So we compute this sigma, see 2a. If you look at the 2a, let's say P2 is A. So sigma P2a, right? That means this is sigma P2 is ABA. So of course this ABA completely is matching with the prefix of this. So its value is 3. So in this similar fashion, we are going to compute this table, and up to 7, we are going to get this up to 7. From 7, of course, A, you are getting 1 and then 2. So this table is being computed. After computing this table, we start from this text. This is the text, okay, and this is the pattern. We start from 0, okay. We start from 0. See, state number 0, and looking at 0A, 0A is 1. So this is noted 1. Then 1B, 1B is 2, yes. Then 2A is 3, yes. And then 2, 4. Then 3, 4. 3B is 4, yes. 4A is 5, yes. 4A is 5. Then 5B is saying we should go back to 4. Yes, 5B we are going back to 4. Yes. So similarly, and then 5C is going to be 6. Yes, this is 6. Clear? And then 6A is going to be 7. Whenever you get pattern length, this state M, it is equal to the pattern length. That means pattern is going to be like found. So what is its location? Look at here, class. 9, you are getting this 7 at 9th position. 9 minus pattern length, and its length is 7. So 9 minus 7 is 2. That means 2 is the valid shift. 2 is the valid shift. 2 is the valid shift. Yes, of course. 2 after second one, you see, this is the valid shift. We got it. So again 7B. So 7B is going to be 2. Yes. So that means 2. That means you are going again back. See, AB was already there. So it is not going to match it again. So this is going to be like again here, and then you start matching again. So then 2A is 3. So this is very powerful finite automata, which is basically like taking the part of the prefix which is also suffix. So generally we are not matching any part which is prefix also. So yes. So this is another example. You can check it over here. See, like it's very good one. A, B, C, A, B. If you want to get A, B, C, A, B. So first one, make a finite automata. Let's say we are starting from 0. States are 1. Okay. And then 2, and then 3, then 4. 0, 1, 2, 3, 4, 5. 5, 4, and then see 1, 2, 3, 4, 5, 6, 7. 0. This is 0. Then 1, 2, 3, 4, 5, 6, 7. This is the situation. So if you look at here, sigma 0A is like 1. How? Sigma 0A, delta 0A is sigma P0. P0 is epsilon. So of course sigma A is like suffixes are A and epsilon. So this is prefix also. So its value is going to be 1. Rest one is 0 and 0. because B is not prefix of the pattern, C is not prefix of the pattern. Let's take this one as random. Yeah, 2C. C like delta P2C. So this is going to be sigma P2C. Okay, sigma P2 is AB. Clear? P2 means AB, then C. So its suffixes are, what are suffixes? C, then BC, then ABC, and epsilon is the trivial suffix. So of course this ABC is part of the prefix. So complete it is going to be 3. Yes. So in similar way, you can compute this. Once you have computed, apply this algorithm to get pattern inside the text. So this is the good algorithms. And okay. In the similar category, if you look at here, what is the drawback of the finite automata? It's just like its space is the problem. You know, we have to consume lot of space to store the states of the finite automata. So that storage requirement is going to be solved by the other algorithm, which we call it Rabin-Karp algorithm. It is now based on the fingerprinting actually. See, so the Rabin-Karp is actually like using theta m in processing. Same thing, this Rabin-Karp is also using pre-processing and matching. This is also using 2 steps, right? So, but in the Rabin-Karp algorithm, generally our pattern and text, they are going to be the number, not like text. Even if you have text, convert it into the number. Yeah. So, and sometime we call it like algorithm based on the concept of hashing. This algorithm is based on the concept of the hashing, right? Yeah. So what we are going to have, like let us assume that pattern, as I said, that is number from 0 to 9, and we call radix of this as d equal to 10. And similarly, we are also taking text from the same like 0 to 9. So in this notation, we are assuming that P represent decimal value, highest value of the pattern. Similarly, TS denote highest value of text, S plus 1 to S plus M. So this is going to be denoted as this. So principle behind Rabin-Karp algorithm is that if you match P and TS, right? So if they are equal, then there is possibility of the matching, right? Then we have to check one by one. If TS is not equal to P, that means definitely text is not going to be, pattern is not going to be matched inside the text. So this is important step to throw out all the invalid shift in the first attempt. Yeah. So basically this algorithm is based on the concept of the Horner's rule for evaluating polynomials. Horner rule is like just like to minimize the multiplication. See how it is going to be used. Like suppose we are interested in computing 215. And we know that how to compute it. 5 into 10 to the power 0 plus 1 into 10 to the power 1 plus 2 into 10 to the power 2. If you look at here, so so this is nothing but 5 plus 1 into 10 plus 2 into 10 square. So this can be represented like 5 plus take 10 outside, 1 plus take 10 outside 2. In this one, there is no difference in the calculation, but only we are minimizing the number of multiplication, right? Like how many multiplication do we have here? Plus 2 times 10 times 10. So you have 1, 2, 3 multiplication. But number of multiplication here are only 2. So this algorithm is using Horner rule to just minimize the number of multiplication. You know that there is no effect in the answer. It is 20 plus 121 plus 10. It is 210 plus 5. So you are still getting the same number 215. So what we are going to have actually here. So this is like working on this concept like to compute the we assume that if we have T0 already and we have P already, so T1 and T2 can be computed using the same rules, right? See, so for example, this is the formula Ts plus 1 is 10. So let's have one example, like see, suppose we have our text like number, let's say 2145, right? So here what we are working on this like and this is the number 214. So this algorithm like how to know the next number. So definitely if you want to know the next number and suppose that you have already processed 214, in order to know the next number, what you are going to have, this 214 is the old number. So subtract this from the old number 2, and you see this is 3 digit, 3 numbers, we are having 3 digit. So just multiply by 100. So it will become subtracting this 2 from this. Okay. So you have subtracted the first one, most significant from this, and then multiply by 10. 10 why? Because radix is 10. So it is like you see 14 140, and then plus is going to be added with this number, so plus 5. So that is the concept, and by this one you are going to get 145. That is the idea behind the Robin-Karp algorithm, right? Yeah. So it is easily based on this. Okay. So what about question is that suppose you have very big value of P and Ts, and you cannot work with the very large number, right? So what Robin-Karp has done, they used to reduce this number to a small number. So they are working on the modulo arithmetic. So they will reduce the pattern and they will reduce the text also. Once you have reduced it, and that reduction hash value is going to be compared, right? Yeah. So this is the formula. Part you already know the Ts. So this Ts plus 1, D is radix, just like I did this one. Subtract the MSB from here. H is congruent to D to the power this. This is highest value. D is radix. M is number of digit in the pattern minus 1 modulo Q. Once you calculate it, multiply, and then this is the one. Lastly, you can compute again modulo Q. So why we need it? This is, as I said, that if pattern is equal to text, is okay. We are going to search one by one. If P is not going to be text, definitely. So this is like going to just tell you that, okay, there is no possibility of pattern equal to the text. So what you are going to have, take the small value, hash value of this TS means valid shift TS, and pattern hash value is already being computed, and take modulo Q. Generally, Q is used to be a prime number. If this is not equal, definitely that means there is no possibility of pattern being equal to T. However, if this is equal, so still you need to check whether pattern is equal to text or not, because you cannot rely on the hash value, right? So two different pattern and text can have the same value. Like see, suppose you have 4 modulo 2 equal to 0 and 6 modulo 2 equal to 0 also, but 6 and 4 they are not equal. So based on this concept, so there is concept of spurious hit, like if their Ts and P are equal, if Ts and P are equal, but text S plus 1, S plus M is not equal to pattern 1 to M, then that will be treated as a spurious hit. Let's see. Suppose like in the same situation, suppose 1412152 you have here, right? And we are computing pattern is like 31415. Take its modulo 13. Yeah, modulo 13. So its modulo 13 is computed as 7. Okay, so suppose you have, and you want to get the new one. You see, you want to 3 1 4 1 5, you are here, and you want to get the new one. So of course you are not going to compute entire pattern again. So what you should do in order to get next one, okay, so what you should do, its hash value 7 minus next value is this LSB is 3 into, and H is computed as 10 to the power minus M. M is like 4 modulo Q 13, and you will see that once you compute it, its value is 3 actually. You just compute modulo 3. So 7 minus 3 into 3, right? And plus 2. 2 is the next member. Okay, plus 2. You see here. So now this is 7 minus 9. 7 minus 9 into 10. Okay, plus 2. So this is minus 20. Okay, plus 2 means minus 18. Modulo 13. You know the modulo arithmetic. Remainder cannot be negative. So if you divide 13, then minus 18. So this is like 26. Yeah. So minus 26. So this is like 8. Answer is going to be 8. Remainder cannot be negative, right? So this is 8. So you are getting 8 again. So you are comparing 7 with this is valid match, but it is 8 is not 7. Similarly, 4 is not 7. Keep checking. And now again 7 is equal to 7. But on the checking this shift, we got that this is exactly not equal to the text. So it is very efficient because of this modulo arithmetic. Whenever you are getting the pattern is like this value equal to the previous computed value of the pattern, you need to check one by one. So this is the Robin-Karp algorithm. Is like same thing which I explained over here. Checking just like valid shift for all the matches. This is important question. Every time it is asking like pattern, they will give Q, right? Q is given, and question is that how many spurious hit you are going to get. So you will see that you will start from this 31 modulo 11 not equal to like your pattern is 26. So 26 modulo 11 you can check 11 like 11 to like 4. Answer is 4. So you keep checking this. Every slot you keep checking. Since text is small, you will get that 26 is the match. Rest value is going to be spurious hit. Yes. These are the references. Thank you for watching.